All right. So today we will speak about other further applications of graphs in NLP. In particular, we'll speak about various technologies which allow you to learn representations of nodes in some linguistic graphs. This material is studied by entire branch of data science. Learning of graph representations is a very active and hot topic. There are even an entire course by Stanford on network science, and this particular lecture is based on some of these materials. I'll try to put it into the perspective of NLP, some of these technologies. Why would you learn? Why would you care about learning such kind of representations for solving tasks which deal with language? Okay, so the structure of our talk today will be like this. So first we will speak about various linguistic networks which are available overall. And then we will present a few approaches, like shallow approaches, shallow models, which can learn node embeddings, node representations, starting from the earliest approach, deep work, and then go into more recent approaches, which feature additional properties and functions which were not available in the earliest approach. And this third block of this lecture will be about deep representations, which rely on more complex architectures. So we will consider three of them: graph convolution networks, graph stage, and graph attention networks. And finally, we will conclude this lecture with some examples of applications of such kind of techniques. Okay, so I can see that everybody can hear and see everything, so that's good. All right, so here's a few examples of semantic graphs which you can find in NLP in various types of linguistic data. So words can be organized in some kind of hierarchy. In this hierarchy, also called taxonomy, it has a certain word as a node, and then these words are basically connected to their parents. So some nodes which have more general meaning. So car is some kind of means of transport, and then automobile is also some kind of a means of transport. But so these relations, these taxonomic relations, they called hyponyms, and they can be used to abstract the meaning of the words. But there are some other relations in semantic networks which not directed, so they are called synonymy. So the meaning of certain word can be equivalent to the meaning of other word, and basically this relation can be considered as unidirected, undirected, or bidirectional, as the meaning of automobile is more or less the same thing as meaning of car. And you will find this kind of links in various dictionaries or lexical databases which organize language. And they have been used on a variety of different applications. And as you can see, as you go to more realistic, let's say, to more realistic applications, or more realistic networks, even if you expand a few words, you will see that this language would directly exhibit this network structure with only if you consider these two types of relations, synonym and hyponymy. You will see a very rich structure of relations across these various concepts. So this obviously would scale even more if you consider more words. So this means that lexical units in the language, they can be considered as some kind of a network. And this representation is very commonly used to think of words and their relations to and their meaning. Another different type of graphs is distributional kind of graphs derived from word-of-vec or distributional thesauri, like those we've seen on the last lecture, last Thursday. So in this case, what you have is a certain word, and then you have a list, let's say top 10 nearest neighbors according to word-of-vec or fast text. And these nearest neighbors, they, well, if you not just get a list of them, but if you build a graph out of them, and then if you make like a second order relations, so if you take then if you draw an edge, if two words in this list are symmetrically related, you will obtain some kind of an ego network for a given word. And an interesting thing is that if you just exclude this word from this ego network, what you can get, for instance, is some kind of a set of word senses. So, for instance, this word sense would correspond to some data sense, and this cluster would correspond to some furniture sense of this word. So this might be very useful for deriving automatically word senses, and people actually do use these representations for analysis and automatic induction for words and of senses of these different words. And again, you rely on this graph metaphor here. Another useful and common type of linguistic networks is entity and word co-occurrence networks. What are these? Well, you can have a text like this one, and in this text, what you basically have, you observe one entity and then another entity. In this case, these are just names of some German politicians, football players, and just the fact they co-occur might be counted. So you might build a network. This is why this network is called co-occurrence networks. You might build a network which has a link between one entity and another entity if they co-occur, let's say, in 10 different texts together. So if this football player and this football player if they are connected, this means that they co-occur in different texts. And based on this property, you can create some kind of a graph and perform, let's say, visual analytics analysis of which entities of words are connected to or co-occur in the media, in texts with others entities in text. So this might be a quite useful tool for building these interactive graphs if you rely on this statistic hypothesis. And here's just another example of a similar entity co-occurrence network. This network is built using this network of the day tool, which is which has been proposed by German colleagues. And what this tool does is basically takes a bunch of news and it extracts entities in this news, and it would build a network which represent a picture of the news for today on the basis of co-occurrences of named entities or in this media. So let's say if Vladimir Putin met Erdogan or spoke to Erdogan, then in many medias mention in the same news these two entities, then you can create a network and then uh, visualize what happened, and then these networks can be further analyzed. Which are, let's say, which organizations and politicians and entities co-occur together. So this might be a way to make explicit and what happening in the news today, but these kind of co-occurrence networks not at all necessarily should rely on entities. They might rely on just words. And in this case, what you will obtain, a graph of semantically related words, basically. And this graph of semantically related words can be used to perform some analysis of words which occur together, and this is quite common to do to build that kind of networks. Another kind of semantic networks and linguistic networks, and they second order linguistic networks which rely on a distributional similarity of words. So this is similar to the ego network approach I shown you a few slides ago, but in this case, this network is built for an entire language. So for instance, this slide shows connections between all words in English language. Let's say you have a cluster here, and this cluster shows maybe all diseases or all United States or names of the cities, and you see that there is a very tight connection between them, or maybe this cluster would link which would contain a bunch of days of weeks and or maybe car brands, and so this might be something like a set of diseases, like names of all diseases in language. And of course there is also this kind of core structure of language where it's hard to distinguish to find this kind of monosemous clusters because the core part of the language is still highly polysemous. So you have a lot of words which which do not which are highly polysemous. So it's hard to split them completely. So this picture is illustrating how entire language can be visualized, and well, the language, you can think of a language as a set of interrelated meanings of words. And so I hope I convince you that it's kind of an inherently useful paradigm and tool, network representation to describe what's happening in the language. Here's just a zoom of a part of one of these clusters, and you can see that you see different types of diseases like cholera, inflammation, influenza, and you see that distributionally, all of these are highly related to. So yeah, leukemia, and you see that if you plot all of them, you will obtain like a graph of highly connected words. Of course, there are some ambiguous words on periphery of this network, which might not even fall into this kind of maybe not even fall into this cluster like this word and this word, but overall, yeah, this is how you can represent things in language. Okay. Another kind of graphs which you might observe in NLP, they are graph of these are graphs of syntactic triples. So in this paper, what we showed with Dmitry earlier is that you can build graphs of syntactic triples, triples which come from some kind of dependency parser, and then you can perform disambiguation of these triples to perform induction of semantic frames. So if you have like an ambiguous triple like government-run market, it can be interpreted in two ways. Maybe government performs some kind of protection or just administration, regulation of a market, and yeah, then maybe just government just perform some operational management of something. So you can perform, you can build a graph out of it and derive some useful structures which correspond to semantic frames out of it. And the list would not be complete without mentioning of syntactic, more common syntactic trees. Syntactic tree is also kind of a graph. And in this graph, well, you often have a tree structure. So you have some root in the constituency parsing. You have some kind of decomposition of different chunks into smaller and smaller parts until they reach some basic units like nodes. In dependency formalism, you usually have these triples. So you have, let's say, a noun modifier, which is like a label of an edge, and then you have two a source and destination, and you can think of it as some labeled edge. So let's say in this case, the word there modifies noun board. And then, well, you can think of this construction, of course, as some kind of a label graph. And you can use it for something useful, like information extraction. And this kind of syntactic trees, they can be analyzed individually, but you can also think of them as a collection of different trees in a large text. So in this case, what you see several trees, and these different trees, well, they basically connected to one another with this discourse relation. So if you see people here, well, it refers to citizen in another sentence. And then if you have like a large text, you can represent them this text as a bunch of syntactic trees, which are interconnected to one another, either through some surface matches. So, for instance, in one tree, you can have person or people, and in another tree also you have a person or people, and that might be just giving you information that this is the same entity, so you can make some kind of connection. Or if the situation is more complex, that the surface form might be different, you can still perform some coreference resolution. Let's say you say like president, but then on another sentence it's like he. And using some methods like coreference resolution, you can still assume that these two mentions are the same. And this kind of syntactic structure, sometimes called parse thicket. So it's a bunch of syntactic trees which are interconnected to one another. And again, you see here some tree structure, some network structure where we have lots of nodes and lots of different relations between them which are connected to one another. Okay, this is another example. And WordNet is a manually built lexical syntactic tree where again you have this taxonomic structure. So let's say you have a golf cart, and then golf cart is a kind of a motor vehicle, and motor vehicle is a kind of self-propelled vehicle, and self-propelled vehicle is a kind of wheeled vehicle. And you might even continue this. Wheeled vehicle is maybe something like an object or vehicle, and again you can represent the semantics of different words through these relations. And what is important is that often in this kind of graphs, relations can be of different types. Let's say a wheeled vehicle has brake, and then wheel, and then splasher. And actually in this is a not complete graph, because the brake itself, it will be some kind of a notion which is less specific than some other notion. Let's say like a braking device. And braking device is also some kind of a device, and so on and so forth. So this is how people get used to structure knowledge about language, to decompose their knowledge about language, describe it, and this is through some symbolic graph representations. One of these ultimate most comprehensive forms of these symbolic graph representations used to represent knowledge about language is knowledge bases, such as Wikidata and also DBpedia. So you have this project called DBpedia, which is more or less equivalent to, in the idea, to Wiki, what Wikidata does now, but it basically was created a bit earlier, and then Wikidata was like an official version of this efforts to create some kind of structured database, structured knowledge base out of knowledge, unstructured knowledge contained in Wikipedia. So what this knowledge base usually is, so it consists of nodes which are entities. Let's say San Francisco. Every entity in Wikidata has this identifier like Q62. So San Francisco is entity number 62, and then California is entity number 99, and so on and so forth, right? And then every such kind of node, every such kind of entity is going to have relations with other entities or other values. In this case, relation is just to a number, so it's not really an entity, and of type population. And then this is a relation between San Francisco and of type in, and then you have this mayor relation, and so they could be like from 1 to maybe like 5, let's say 5,000 of different types of such kind of relations, which means, yeah, it's a lot of different types, and you can not just represent them as a binary graph. So if you just forget about all of these relations, well, you still have this backbone of this graph, and it can be still useful. But obviously, in this case, if you have just this kind of the directed graph, you cannot answer the questions like who is the mayor of a city in United States with a population more than 300,000 people. Give me all mayors of your cities with such kind of population. If you have these types of relations, then you are able to perform some kind of a structured query on this database and say, hey, I have United States, and then I can retrieve all the cities, United States cities, and then I check whether a population of a city is more or less than 500,000 K, and if it's more than 500,000 K, then I retrieve another property, which is the mayor, and I output it, right? But in case if it's just this simple graph, you're not able to do this kind of query. So that's why knowledge bases are very important and very useful things. All right. So let me ask if there are any questions about this first some usefulness of linguistic graphs. Maybe somebody heard of some other useful graphs which were not mentioned. Okay, so if this is not the case, then let's continue the lecture with some methods which you can apply to learn some representations of this kind of networks. And what is the point actually to learn at all these representations? What is the goal? As you've seen, many linguistic phenomena can be represented as networks, but usual representation for the networks is adjacency matrix. So it's a kind of a sparse data structure where you have basically every node as a row and some non-zero value on the intersection of row and column if there is a certain link between them. So if we have I and G, nodes I and G, then non-zero element in this matrix would mean that there is a link from I to G, and if the matrix is symmetric, then like in this case, you will see that these relations, this graph is undirected. So if you have a link from I to G, this implies that you have it to G to I. But it's not always the case. If you have graphs like taxonomies, yeah, this would mean that you have inherently asymmetric matrix. Now, what is the problem with this matrix is that it's a very sparse. So if you have, let's say, large network, if you have language, you may have, let's say, 300,000 of unique words in your dictionary. So then you have 300,000 by 300,000 adjacency matrix. So this is huge. And consumption of representations in this form by some kind of algorithm start to be also problematic with this sparse curse of dimensionality. So this is the same problem as the one we've seen with sparse vector spaces such as TF-IDF and the like. So you barely can obtain some generalization. So that's why people started to try to learn some kind of representations where this size of with a number of dimensions d is much less than the size of this vocabulary. So this is really the key idea of any node and network embedding approaches, so that you learn something which is not sparse but rather dense, and this can be used to obtain some useful representations which allow you to represent the nodes, so words or syntactic constructs, and then you can perform something like clustering or link prediction in these linguistic networks using your favorite algorithms, right? Because the majority of algorithms for machine learning data analysis, they kind of expect this matrix with a set of features, right? And if you provide this insane number of sparse features, the majority of them won't give you good results, won't generalize, won't be able to learn, let's say, weights for each of these 300,000 features and so on and so forth. So graphs are good, but this direct representation isn't useful to combine it with machine learning things. That's why you need this kind of network embeddings. And really, the idea of network embeddings is that you have this network. In this case, it's a very small network from karate club network. So actually, every person is some person attending offline club for karate. And then this are kind of connections for a friendship connections between people in this club. And you see that if you apply algorithms such as Chinese whispers or Markov clustering, you can perform segmentation of this graph into several clusters. So you see different groups of people in this club, And you see that, let's say node 17 is in vicinity of node 7 and node 6 and node 11 and so on and so forth, right? And what you really ultimately want to get with some of these approaches, some of node embedding approaches, well, you want to get a vector space. In this case, it's just a two-dimensional visualization. So, but in reality, it will have dimensionality similar to dimensionality of Word2Vec. So something from, let's say, 50 to 300 will be like a reasonable number of dimensions. And so you want to get this vector space where guys in these clusters, they're going to still be close according to some metric in this space, let's say Euclidean distance or cosine distance, Manhattan distance, something like this. Obviously, if you just, let's say, initialize a random vector to each of these guys, what you're going to get is a bunch of random, like a mixed bunch of mixed dots here, which do not semantically represent well the original structure. So this is the main challenge of how to learn this so that original distances in the graph are preserved. And one of early approaches to solve this task was the approach by Pirozzi et al. Called DPOC, proposed for 2014 at KDD, which is a kind of top tier data mining conference. So right, so here the goal is to learn given a network and for every node of this network to learn a function which would project the node into this d-dimensional space with a small dimension. And then these feature vectors, you can think of them as feature vectors of Word2Vec embeddings, right? So you can have some word, you can obtain a vector, perform lookup of their features, and then do something useful about it. So the same idea would be applicable to graphs. So in this case, is a very similar. The only difference is that in the approaches before, an item, a symbolic item, which originally would be represented with one hot encoding will be a word, but in a graph, a symbolic item which is represented with one hot encoding originally is a node, right? In the vector space, like sparse vector space, this one hot encoding would often correspond to some co-occurrences within the document or some context word, and the graph would, for graph, direct links of this node to other nodes, they will be these sparse features which would characterize this node. But then otherwise technically is very similar. If you have any questions, so feel free to interrupt me. It's no problem. And okay, so given this task, the main challenge will be to learn such an encoder for the nodes, which will, as I mentioned earlier, not only give you some vector presentations, but also preserve the fact that the original graph, in the original graph, these two different nodes were close. And the common is to use dot product or cosine similarity, which is normalized dot product basically. But also other common notions of similarity or distance, such as Euclidean distance, might be applied at this point as a measure of success for this kind of an embedding. So for each node, you're going to have like a vector which would represent this node. While it's yeah, the key question here first will be how to define the similarity function, and then if you can use just simple product between vectors, meaning that two nodes are similar if they have lots of common features of similar profiles, right? But this is not only a thing you have to define, you have also to define some kind of an encoder, which would rely on this similarity function, and then well, as you define the encoder, the mapping, you and the similarity function, you have to optimize the parameters of this encoder so that the similarity of the original network is going to be very similar to similarities in the embedding space. So once again, yes, what you get as an encoder as input, you're going to have this symbolic representation. So you're going to have a node, and then the output is some kind of a vector. And as output of the shallow approaches, what you usually obtain is more or less the same as what you obtain by training word-back. So this is some kind of a matrix of dimensionality d by the size of the vocabulary. And then you can have like indicator vector, which is just non-zero at one position, and which has dimensionality equal to the size of the vocabulary. And by performing a matrix product of this vector, what you can just trivially retrieve, you can retrieve embedding of a given node, right? As all other elements, there will be of the indicator beta 0. All right, and so yeah, this basically would look, this embedding matrix would look like this. So you are having as many columns as you have nodes in your network, and then this dimension will be small, much smaller usually. So it represents k, which as I told, is something like 50 to 300, maybe a bit more, maybe a bit less, but is usually This k is usually much less than this size of the vocabulary. We will start our discussion with two approaches. The deep work, one of early popular approaches, proposed shortly after Waterweg. So Waterweg was proposed in 2013, and deep work has been proposed 2014. And then another approach, which basically is very similar to deep work, called Not-to-Work. It was proposed 2 years later, and it introduces some improvements over deep work in the way it would is going to sample features while training. But conceptually, these two approaches are very similar to one another, and they're basically extremely influenced by the original Word2Vec approach by Mikhailov. So that's why it will be quite easy to you to grasp how they work, as you already know about Word2Vec. All right, so it's 5 o'clock. Maybe I propose to make some 5-minute break, which is deep work. And deep work is based on random walk. Given a graph, random walk of length k is some kind of stochastic process where you have associated with k random variables, such that the first one is initialized with some started value of this walk, and then next random variable is chosen uniformly at random. The value of the other random variable is chosen at random on the basis of neighborhood of certain value, certain random variable. Let's say we have this node, and then you're going to have a random variable associated with this node, and then you have only two nodes associated with this one, and there might be some probability associated with each of these edges. If you don't have any weights, then the probability will be just proportional to 1 divided by n for this node, where n is just the degree of this node. Okay, sorry, so there are actually three edges. So in this case, maybe in this, for some reason, you have just 0 probability of going here if you go to sum to 1. Or you just have something like 0.33 here, and then 0.33 here, and then 0.33 here, which would correspond to this formula. Then what you're going to do, you select the value of this random variable according to this transition probabilities. So you just toss a coin, and it appears that you are going to perform the transition to the node 1. So in this case, the value of this random variable, it will be 1. But with equivalent probability. It can be 3 or 5. So and then the procedure repeats. So as E becomes this state, this node, then in this node you have two options, and you have associated probabilities with going in this direction and this direction, and then you're gonna do a coin, and then you perform a walk, another step of the walk, and then what happens is that you're going to have this sequence of steps in your graph which you performed. And let's say if you have a random walk of 5, k equal 5, then you're going to have these 5 visited nodes. And what you can do, you can initialize several times these walks, and as this is a stochastic process, obviously you might end up with different paths. Let's say if you have this random walk with 5 k equal 5, then it may happen that at some point you get into this triangle, and then maybe you visited this node twice. So you went here, and then you went here, and then here, and then you return to this node. So that might be another random walk which you performed on this graph. And so as a result, what you're going to have, you have a sequence of points selected in this way, which you're interested in, right? And this random walk is usually based on you use this transition matrix to perform it, but it's basically technicality. And really the key observation which people proposed and which was the key innovation is that you can use these random walks as a notion of co-occurrence of different nodes. So if you have a sequence of steps, let's say for this case of 5 different nodes, and then you have a node U here and node V here, then you say that these two guys are going to be connected. If you have you never observe, let's say, the node K here in any random walk, that would mean that K is supposed to be not connected to U. And this is very similar to what we have in What2Vec. And so in Walk2Vec we have some kind of a word. And then you have a context. So here's first context word, second context word, third context word, fourth context word, right? And here what you're going to have, like first node, second node, third node, and fourth node. So this is like context word, context word, context word, context word, and this is context node, context node, context node, context node. And the difference, of course, is just how do you obtain these context words. In the case of What2Vec, we say, hey, these guys should be inside of some context window. So let's say we have a text, like running text, And then we have this sliding window, and these guys are connected if we just have this co-occurrence of this context word inside in the just vicinity, in textual vicinity. And in case of graph, you don't really have this linear structure. You have the linear structure, and instead what you do, you substitute these linear structures with this short, so basically you kind of generate these context windows, linear structures through these random walks, and then the rest is more or less the same. So you assume that these guys are connected, these guys are connected, these guys are connected, and the four vector representations or dot products of this node and 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 this node, they have to be similar. They have to be close in the vector space you're going to learn to one another. All right. So interrupt me if you have any questions, but yeah. So yeah, in this case, what you're going to do, you're going to estimate this probability of visiting one node on some random walk and optimize embedding such that this distance probability of, given that you are in one node, will be high of visiting another node in case they are indeed observed in some real walk. And for other pairs of nodes, this probability should be small. Assume that you have some completely unconnected part of the graph. So then the probability of visiting, like node K, given node U should be 0 in these embeddings, because there is simply even no path from this part of graph to another part of graph in the model, which is going to assign equivalent probabilities to conditional probabilities to this and this. It won't be a good model. All right. So the main idea is really of this deep approach is to learn node embeddings such that nearby nodes are close in this vector space. And as I mentioned, like really the entire trick is to define the set of a neighborhood for a given node. So the entire idea is to get some contextual nodes which are not necessarily directly connected to this node. This will be trivial. You just get word nodes which are directly connected to a given node, and that's it. But the problem is that it will be insufficient amount of training data, which won't be able to generalize well. Instead, what you do, you get larger context from this random walk thing, and then all of the networks, all of the nodes in this context, they are going to be training signals, training pairs for learning representations of this node. All right. So the main idea would be to, given certain graph, is to learn this mapping and maximize log likelihood of the data. So given some node, we want to maximize a probability of nodes from its vicinity, and probability of seeing here nodes not from its vicinity should be low. If we detail a bit more different steps of this approach, it will look like this. So first you're going to run some short fixed length random walks on the graph for every node. So then the output of these will be some collection of training instances, training contextual features for this node. And yeah, this is a multi-set because you obviously, as we've seen, you can reach, starting from one node, you can reach the same node several times and on these walks, and this is completely normal. This is the same as observing, let's say, the same word in Word2Vec as context. You can have a word there, and even in the same context, if this is a target word, you can have a context, and then this word shows, let's say, twice. It might be very well the fact that this is a good feature, in fact, for this one. Okay. And then, yeah, given these collected features, you have to maximize the objective we mentioned. So more specifically, what you're going to do, as we mentioned, you're going to iterate through all nodes in the graph. So you're going to compute this well, logarithm probability for all nodes, but also you're going to iterate through all contexts, contextual nodes from all elements in this neighborhood, right? So at each element of this iteration, you will have something like a context word pair, similar to skipgram of Word2Vec, where you have also pairs of target word and the pairs of context. In this case, this context is this, and target word is this. And similarly, again, to Word2Vec, an easy way to turn this dot product into probability would be a softmax, but similarly as also to Word2Vec, this component is really problematic, because just to compare, if you have, you would have like another sum here at every point of time. and that would be kind of a cubic complexity for each step. You will have to perform this computation again and to renormalize the probability, which is quite painful to do. This is why you don't really want to have this component. It's you can really get rid of this component and this component. This is similar to Word2Vec, but similarly to skip-gram negative sampling approach, which we studied on the second lecture. There is a need to overcome this computational bottleneck. So this, otherwise, it will mean that you have this v-squared complexity multiplied by some constant, which is, let's say, an average number of nodes in your vicinity, which, again, if your walks are large, might be also quite large amount. And yeah, this is why I say that deep walk and Word2Vec as well, they are conceptually extremely similar to Word2Vec. Well, this is why because they adopt the same idea of negative sampling, which is a kind of noise constructive estimation approach to approximate this probability. And to do this, what is suggested by these approaches is to generate from some random distribution, which is proportional to just a distribution across all of the nodes. It's proposed to generate several negative samples. In this case, it's like k negative samples for each positive training example. And in this case, this probability is going to factor into a logarithm of sigmoid of this dot product and a logarithm and the sum of several logarithm of sigmoids for several negative examples. And this means that you replace this v by small k, where k is much less than v, which is why it's so much more interesting to do than directly compute this sum. The usual number is going to be, for k, is going to be 5 to 20, which is maybe also similar to what you obtain in Word2Vec. So in short, what you have to do to train this deep walk approach, first you run this short fixed length random walks. Then for each node you collect neighborhood, and then you optimize this negative log likelihood criteria loss function using stochastic gradient descent, or it's just a sum over all nodes and over all context for each node. Okay, so far so good. So let me ask if there is any question at this point about this first approach. If this is not the case, then let's continue. Second approach we're going to discover today is not to vec. The way not to vec really learns embeddings is almost similar to debug. The difference between not to vec and debug comes in the way they generate these random walks. And not to vec parameterizes this procedure by introducing two additional parameters, and it introduces the notion of a biased random walks, which can trade off between local exploration of this neighborhood of target node and global exploration. And yeah, really the main difference is like how breadth first search related to depth first search. These are two classic approaches for performing exploration of the graph. So in BFS, you are going to explore all the neighbors first, right? So, and then once you exhausted all the neighbors, you are going to pick one and then explore all the neighbors of this only one neighbor, and so on and so forth. While in depth first search, you're going to move in certain direction, abandoning and postponing the exploration of direct neighbors, right? And the strategies inherently yield you different kinds of contextual walks, random walks. If you use the first strategy, you will obtain more closely related, directly allocated nodes to the source. In case of other strategy, you're going to explore some long dependencies in this graph. You're going to see how this particular node is related to some other distant nodes. So the main idea of not to vec is that it makes sense to combine these two different strategies to get complementary view on the graph. It's like when you travel somewhere, it makes sense to have like a global map of where you're going to travel, maybe with the large towns and large roads, and then as you plan more concretely where you go and how you reach a destination, you need some kind of a local microscopic view. So this is a reason also why you have different levels of zooms on Google Maps or some other maps, right? So, but obviously the graph is just a static structure. It doesn't have inherently these zoom in, zoom out buttons, and that's why this different exploration strategies they yield different properties of the graph. So BFS rather get you some dark neighborhood, but DFS rather give you some long relations, not directly exploring this direct neighborhood in many cases. So that's why they are different, and that's why, and it usually makes sense to combine something which is inherently different, and this is the case for these DFS, BFS things. And how it is done, well, the authors introduced two parameters, P and Q. And P is a parameter which controls how often you're going to return to the previous node in your random walk. And Q is a parameter which is going to control how much you want to move it outwards from your original destination, how much you're going to explore into the other parts of the graph, rather than further exploring some local neighborhood of this graph. And then by playing with these parameters, you can find essentially some optimal ratio between BFS and DFS strategies while generating these training sequences. And more specifically, these biased random walks, in the case of Node2Vec, they are made through second order random walks. What this means that you have some kind of second order Markov chain, so you have some kind of variable which can look back at two steps back or one step back, one previous step, depending how you define it, right? So the point is that started at some node, you assuming that you made a certain step. In the usual random walk, you're just going to forget immediately this previous step, and you're going to, use these transition probabilities, including the, if it's undirected walk, the probability of going back, but also all of these to make a further decision. It's not the case in this strategy. In this strategy, as you in this node, you're going to remember that you came from this node, and you're going to remember that this node is adjacent with the node you're currently in. So there is basically just a few options you can do here, and this P parameter will influence the probability of returning while you're in this step, while you're in this node, to the node where you have been previously. So assuming that you made this path and you are currently in this node, then the probabilities will be distributed like this. So this will be the probability to return directly from to the position where you've been during the last timestamp. And this node is marked red because it's known to you that it's a kind of a local neighborhood of the node you visited again. So basically going into the direction of this node, meaning that you are not going to explore something completely new. You rather while not going back directly, you can go back in 2 steps to the same node. So that's why this node has this one probability. And then if the Q is very small, then the probability of going into complete unknown part of a graph will be high. So given this explored part of the graph, if you go in this direction, you are sure that you know that it's not possible to reach this step, for instance, in 2 steps. There could be, because there is no direct connection between this and this guy, right? So you cannot reach actually this guy in directly. So that's why this indirectly node which don't have some direct connection with this node, they are considered to move you away from the original node. So this is the main idea. And then just this is how you will convert these probabilities, and then you're going to normalize this into some probability distribution, and then again perform some selection using random like a random guess and make a step. All right, so this concludes part related to Notovec. If you have some questions, let me know. And yeah, assuming that you done all of this random walks, and then you trained some kind of Orthovex style model on this collected contextual graph contextual representations, then what you obtained like a matrix for which represent every node with low dimensional vector. What can you do about it? You can represent the nodes with vectors and run some standard graph clustering algorithm to perform community detection. So this during the last lecture, we've seen that there are specific graph-based algorithms which deal with graphs. So they don't assume any node, any vector representations of node. It is perfectly fine to have such kind of algorithms. It's very useful because you don't need to go through such learning procedures, and then these algorithms might work faster or something like this. But if you have these vector presentations, well, you can just directly apply k-means or affinity propagation, agglomerative clustering, whatever. The very standard algorithms you've seen probably many times in various data science classes without taking any specific properties of these graph structures into account. The same goes for supervised classifiers. So you have a bunch of nodes. These bunch of nodes, they are kind of bunch of features. You pull them one by one, into a classifier, and you get some prediction label. So this might be whatever linguistic properties you want to assign to your linguistic data. Point is that it's not only through word-to-vec or distributional hypothesis you can get this distributional these features of words, of concepts, entities. It's also through these symbolic structures. It might be in addition used as additional features. It might be used as the only source of features. But the big point here is that whatever task you have at hand, where which you can solve with word embeddings, well, the similar task can be solved by replacing word embeddings with node embeddings if you manage to find corresponding network to apply these algorithms. And last but not least, important application is link prediction. Then you actually go on to contribute to your original graph. This means that the graph might be not complete, and let's say you have this graph, and in fact, this edge was not created, but it's actually valid. Well, by using these node representations, you can try to compute similarities between this node and this node, and come to the conclusion that some edge should be constructed in this space. So this is called link prediction thing, and it perfectly works for all of these kind of linguistic networks we discussed before. Okay, so yet another approach which we going to see based on this shallow or not embedding representations is performing metric embedding. You have and probably know some of quite a useful graph metrics, such as the length of shortest path between two nodes. And in case of linguistic graphs, this length it was very actively used for modeling semantic similarity, given some large linguistic network, WordNet, BubbleNet, something like this. You can say that two different concepts are related. They have some meaning, common meaning, in case there is a short path between them, or short path might be useful feature in some kind of formula for computing these graph-based methods for assessing relatedness of nodes. So this is nice, but the problem is that to compute for a pair of nodes, estimate this distance, you have complexity which is proportional to a plus v log v. It is well, if you for very large graphs, it might be quite a large number. And on the other hand, if you have a vector embedding of dimension TD, You can just perform a dot product of one embedding with another embedding, um, and this will be just a sum of their respective products of their respective components. So you have a sum over the elements. And this usually is much less than this. So it might be possible to then learn such kind of graph embedding, node embedding metric, which going to approximate these different metrics such as shortest path. So basically trying to embed these distances into some kind of small dimensional space, low dimensional space. And why this is at all useful? It's also because not only calculating metrics of distances is useful on a graph, but also you can characterize nodes through different centrality metrics. And to compute the centrality metrics, very often you need to know these distances. And one of the common and very useful centrality metric is closeness centrality. Closeness centrality is an average length of the shortest paths between the node and all the other nodes in the graph, which means that you're going for every node you will need to compute all of these distances, which would mean that this number you will have to multiply also by the number of nodes in the graph, by the number of vertices in the graph. So these kind of computations might be useful to define some centrality or some properties of the linguistic graph, but it's very intensive. So that's why path to vec was proposed. Is an approach which encodes distances such as shortest paths, hence the name of the approach, into some low dimensional space. So this is a work with some colleagues, and the idea is actually very simple. What you're going to have, you're going to generate for each pair of the node some real gold standard value of a target metric. And this might be a real shortest path distance between node E and G. Or it might be a value of other more elaborated metric. And then what you're going to have, you're going actually to minimize the objective where you're going to learn such kind of embedding that is minimizing square root loss between dot product of these two embeddings and this target similarity goal similarity value. And this would represent some kind of a global distance in the graph, because these pairs of nodes might be actually not directly connected. They might be located in completely different parts of a graph. And if there is some path between them, you still have to predict it more or less correctly, right? And this objective is further regularized with this local objective, where N and M they are nodes which are directly connected to nodes E and G respectively. So these dot products, therefore, they ensure that not only global structure of the graph is preserved, but also all of these local connections are good. So you have node E, and then you have node G, and what's going to happen is that you will ensure that these nodes like N and then M and others, they will also be similar to this node. So in this case, one node from the local neighborhood is taken at random at each iteration of this approach, and so at some points you will select this node, and at some point N will be this guy, and M will be this guy. But they are always directly connected. So you have this target metric going to learn, but also you have this local neighborhood. So then the graph is preserved in two ways. This idea is somehow similar to the idea of node2vec in the sense that they want to preserve some kind of a balance between exploration of local and global structure of the graph. And computational experiments with some different measures, such as shortest path, but also other more elaborated metrics, such as Wu-Palmer, Lecoq-Chodorov, well, they show that you really gain a lot of computational of improvement in terms of speed. So if we say of shortest path, so this time was constant because it's just a dot product, right? Usually, if you have kind of a dot product between two sparse low-dimensional vectors, whatever the values of the vectors, usually complexity one will be more or less the same, which is not, of course, the case for different metrics. So this way you can approximate some nice graph-based metrics, and this also metric it shows very good correlation with original judgments. So this is another reason you might want to use some node embeddings. All right. Do you have any questions about this? Okay, so I will try then to quickly finish with yet another approach, and then we will have a small break. The last approach is trans-E, and the difference of this approach is that it takes into account not only binary relations, but also it takes into account the fact that graphs can have different relations. Like knowledge graphs, they, as I shown you, they have, Michael Jordan was born in Michigan, or Michael Jordan was play for Chicago Bulls or something like this. And these are not exactly the same links. And the authors of some other group of approaches, what they basically propose is to learn also embeddings of different types, and then by what they suggest is that to do operations similar to this word-to-vec analogy operation. So if we add to king, so if we extract from king man and add queen and add a woman, we're going to have something like queen. Here, if we take Michael Jordan and then we add embedding of play 4, we should have, according to this idea, something like Chicago Bulls. And if we have and we should not have some statement which is not encoded in the real graph. Let's say Michael Jordan plus was born in should not be equivalent to St. Petersburg, which is this entity, this type, because it should be a different entity, so which is present in the knowledge base. And the algorithm trans-E implements this idea in a simple way. So trans-E is just to learn these embeddings through optimization of two matrices, matrix of entities and matrix of these different relations. So every row in this matrix of relation would represent different types of relation. Was born in, married to, went to, died, at some point. They're first initialized just randomly and normalized. Then the training is going to happen, and in a similar way to not-vec, in a similar way to deep work, the idea of negative sampling again is used here. But in this case, the negative sample is, so in case of not-to-vec, negative sample in case of word-to-vec for a given word, we have a true and true context word and random context word. In case of not-to-vec, we have graph, target node, and then some node which you've seen on the path, and then you have this node, and then you have some node which you did not see on this random walk, random path. And here we have this triple, and what you go into do, you go into fix the type of relation, but you go into generate randomly not only these guys, but also you're going to generate the source entity. So you have this corrupted triplet, and then you have a right triplet. And then what you optimize objective where you want to have a small distance between real relations and large distance between some dummy relations. So you have, let's say, h plus L. In reality, it's like equals 2, and then you predicted some it equal T, and then you predicted some value which is close to T. This is good. But if you took some random relation, you added this L, and then you ended up with some completely wild end point in the space, which is not at all correspond to some real relations of this H. Well, this is what you want to optimize. Okay, so this concludes shallow node representation model section. In case you, okay. So we're going to discuss in this part deep node representation models. And first, let's discuss why at all would you want something better than AutoVec and deep work and things like that. What is the problem with this? The problem appears to be in the fact that these representations, they would perform a lookup of embeddings from this table, but you might not simply have for new nodes these records, or these representations also might be not powerful enough for solving some of the tasks. So again, to store information, you need space proportional to the number of nodes. For some graphs, for some linguistic graphs, it might be okay to have, but think of knowledge bases. New entities are created every day on Wikipedia. New properties might be added, new types of nodes. Then this number will be very large, and it might be just not useful for some of the applications. Then another big disadvantage is that you really have to fix the graph beforehand, and if you have a new node joining the network, let's say you have a network which describes words, but then you have a new word, let's say a selfie. A selfie word became popular maybe 2014, 2013. How would you describe this word? Well, you would not be able to look up for this node any embedding. There will be no. And the last shortcoming is that while node embedding generates features, like dynamically, this is nice that you just run this random walks, and then through this information about concurrences, you got information, you got these vectors. Vectors can be used as features, but in some cases you do have features. You already have some features associated with the nodes. Let's say you have these properties of entities. You have different cities, and the cities has every city has a date of a foundation or the number of citizens, and this is like an entity in a knowledge base. But in the case of this usual mathematics, there is no direct way to do to integrate this additional meta information. And what kind of would be nice is to have this graph, and then learn some deeper representation of this graph, which would not be also just like a shallow network like Word2Vec, but would be also in the spirit of more powerful deep models NLP. So that is the idea, but the problem is that graph is not as regular as image or text. If you take image, you have this grid structure. So the convolution operation, which is used in these convolution networks, would be using these patches, and feature of the central pixel will be like some kind of a convolution of features of the pixels around. And if you have text, you have some kind of a sequential structure. But the graph is more complex, so you cannot directly adapt these CNN filters to graph. It's not trivial to define it. And the key observation is that you can also think of this graph as this filter. And information from the neighboring nodes can be used as features. And then what happens is that you can average messages from the neighbor, this ego network, to get representations of the target, of the ego of the target word. So assuming that you have some features and representation from this node and this node and this node, then you can get the messages from your peers and then obtain some representations of your own node. So this is really the key idea, which was first proposed by Kip and Welling at ICLEAR conference, dedicated to learning of various presentations in 2017. And the key innovation here was to actually use structure of the graph as a computational graph. So you build some kind of ego network of a node, and then computational graph is defined on the basis of this ego network. So the features coming from other nodes, they help you to propagate transform information. And in this case, this ego network idea would look like this. So if you have some target node A, well, what you can do, you can kind of unroll its direct neighborhood and local neighborhood into a computational graph. So this will be like a direct neighborhood, which will be depicted here. And then node B, it has its own direct neighborhood, which is A and C, right? And then you have this direct neighborhood of B, and then for C, the same thing. You have direct neighborhood of this guy, right? I'm sorry, and also this node. And then you would create some kind of cascade where you will learn, which will help you to learn feature presentations. of the target node. All right. And this computational graph is defined therefore with a certain depth, like small depth. In this case, it's like ego network of a second order, right? So you take neighbors. So you take the node and then you take direct neighbors, and then neighbors of neighbors. So you don't go further in the network. And the reason you don't go further in the network for building such kind of structures is because of the small world phenomena and of the fact that the diameter of the majority of the graphs is about 6 to 7. So there was even a famous experiment by Milgram in the 30s, and he connected that the majority of people are connected to one another with 6 to 7 handshakes. So you are going to be connected to whatever person in the world on average with this 6, 7 handshakes. And the same property is exhibited by linguistic networks and the majority of naturally occurring networks as well. So that's why if you actually build a network with these, 7 depth, 7 levels of depth, then it will be just the entire graph. So this competition graph will be like massive, enormous, and probably won't be really practical to deal with it. And therefore, what you're going to have, then you're going to have some features of different nodes. And these features, they are going to be combined by some neural networks, or let's say it can be fully connected layer, some other aggregation function. We'll speak later by these aggregation functions. So they are connected through these aggregation functions, and then they are used to predict these features of the target node. And interesting property and very useful property of this construction is that these aggregations should be order invariant because you can rename the nodes in the graph in different order, but the structure of the graph will not change. And this is obviously very different from some images where you cannot just arbitrarily change the pixels, but then the image will be destroyed. But this might be the case for graphs. So every aggregation function has to be order invariant. So the order matters a lot in text, but if you deal with a graph, let's say you have, I don't know, animal, and then animal, there could be two, like let's say cat is animal and the dog is animal, but it doesn't matter whether this node is the first and then this is the second, or vice versa. So this construction allows you to therefore to learn to aggregate information messages from the network, and the main so this is the way how you're going to combine it. So they will be basically two parameters in this combination, b matrix B, which is going to be multiplied by the previous layer, previous state of this embedding, of this node. So if we have layer A, and then you want also to have previous state of this A, previous embedding of the previous layer. And then what you also you have also neighbors of this node, and every neighbor has its own embedding, has its own state, hidden state. And what happens is that you just average these messages and multiply these by another matrix, which says you how much you should take from and what you should take from these neighbors, what kind of messages. So therefore you have two components, how much information you want to get from your own previous state and how much information you want to get from your neighbors. And then just sigmoid is as usual, so also used to normalize these to some probability distribution. All right, so and this can be done at several layers of depth as usual. So the main ingredients, therefore, in this construction are these matrices which decide how information will be combined from the neighbors and from your previous state. And that's basically it. So given some nodes, some ego network, and with some connections, what you will have averaging of the messages from the neighbors in equivalently weighted forms, and then these two sources of information going to be combined to update hidden state of this network. And this construction can be trained in both supervised and supervised way. If it's unsupervised way, this overall thing becomes some kind of auto encoder. So you can again use losses similar to Notewek or Deepwalk. So you generate such embeddings for which dot products of some dot products of node pairs co-occurring in a random walk have high value. So if these pairs belong to some walk, otherwise it should be low, right? But given this objective, it's also alternatively possible to use information direct supervision or direct labels. So you can just have binary labels in this network and to train some usual objectives such as logistic regression objective, cross entropy objective, and maximize these parameters and node embeddings. So parameters of this classification objective, but also this node embedding parameters simultaneously to solve particular task well enough. Okay, and the very nice property of this GCN thing is that now, given some pre-trained matrices W, K, and BK, you are now able to perform encoding for whatever network you have, for whatever new node you have. So assuming that you have some new basketball player in your knowledge base, let's say you had a network like knowledge base which it coded all basketball players and features maybe of all baseball teams and some other sport things. Then a new basketball player joins, and you know that this guy is a kind of a basketball player, and this guy was born in Chicago, Illinois, and this guy plays for Chicago Bulls as well. Given this structure, new network for this guy, you can use these matrices to perform encoding and obtaining node embedding for this new node, for this node. And this is very different from a lookup from some pre-trained node vec or deep-work table, where you will simply not have any entry for this new basketball player, right? So this is a nice property which enables you some inductive capability. So of course, to be able to use this property, you have to link these new nodes. And of course, distribution of the new ego network should be somehow similar to what you've seen during the training. If you just have a new node and which is not connected to anything, then there might be some other approaches to still encode it. Let's say you can have some features attached to the new node, but not links. Well, it still might be possible to use this encoder, but in principle, it's better that you have this new node connected. All right, so let's quickly look at a couple of more models which improve a bit over this baseline GCN model. Another model is GraphSage, and basically it improves the way how aggregation of the messages can be done. In this case, in the previous case, in the case of GCN, it's just an average, right? So you have messages of previous hidden states of this guy and this guy, and then you just perform this average, unweighted average, and you use this information. So you perform some nonlinear transformation, some multiplication of this aggregate information by some weighted some matrix. But then aggregation is done through simple average. Now, in this approach, they generalize this idea. They tried several different aggregation methods. Yes, the aggregation method in principle is going to take um, for a given node several neighborhood nodes, and then they're going to do something and return some other vector value. So given a list of vectors as input of different lengths, this list can be of different lengths, it's going to return you some single vector. And obviously there is also several ways, several functions or approaches which can solve this purpose. This is the simplest one, right? So this is what we've seen in GCN. You just go into perform the aggregation by averaging. But you can also can perform maximum value, or you can have particular transformation for each neighbor. So this would be some generalized form of pooling. And further, you can even consider this sequence of hidden states or neighbor vectors which correspond to some messages from neighbors, the sequence, and then you can treat this sequence with some neural network, which such as LSTM, and then would allow some non-linearities, non-linear transformation between these input messages and the output. So this is the main difference between gross age. So trying to get more kinds of aggregation. And another improvement to these several architectures was to rely on attention mechanism. And again, let's look at this simple aggregation method. So what it does, it is going to just perform the sum. And in the sum, every neighbor will have the same weight. This is not really optimal approach, as it might be that you might want to inherit more information from neighbors which are more similar to you. If you have, if you are connected to, let's say, some neighbor which has almost the same socio-demographic profile, and then maybe these features of this neighbor are much more important than features of some other neighbor which is also connected to you, but for some kind of random reason he's not very similar to you. And then the idea becomes to introduce some explicitly some weight between this node and this node, right? So this sum therefore becomes weighted as before. The weight is just 1 divided by n. But this weight might really depend on the node. And then this arbitrary importances, they're also going to be learned for some attention strategies. Let's say if you have certain message already has in state, nodes which are similar, which carry similar signal, for instance, they have to be considered more seriously than some other nodes. It's like, think of you choosing some product and you are going to take some advice from from your friends and some other people on the street. Maybe your friends are more similar to you, and you're going to take into consideration better these messages. And so this attention might be considered as some kind of a function which takes as input hidden states of one and another nodes, and it performs some transformation of these hidden states and outputs some value which characterizes similarity of these two nodes. And then attention value will be proportional to this unbounded value, so it can be just normalized using usual softmax. And yeah, this is basically it. So there is these coefficients. They can be used in the sum, and they can be learned as a part of the network. So yeah, that would allow you to further improve performance of this kind of networks, to not just blindly average over all messages coming from all the neighbors, but also take into consideration some kind of similarity between the neighbors. And of course, on the top of it, you can also, if the graph is weighted, you can also take into consideration weights of the graph. But again, these two things, they are kind of orthogonal, so you can take into consideration weights in the sum, but you can also take into consideration these attention things. Okay. This concludes the methodological part of the lecture, and then we are going to have a short overview of various applications, NLP applications of this technology. The first application I'm going to show you, it was published at last year at ACL conference, related to entity linking. And entity linking is a task where you need to disambiguate words in context. Let's say you have Michael Jordan, football player, Michael Jordan, basketball player, Michael Jordan, mathematician. And if you have a context, you have to tell which entity you are seeing now. And the state-of-the-art approach to solve this task, they rely on some kind of text embeddings and end-to-end LSTM-based system where text is encoded, the context is encoded, and then disambiguation of these three candidates is performed. So let's say you have some vector of context which correspond to a text, and then you have a vector like a network embedding which correspond to this guy and this guy and this guy. And what this network, what this end-to-end system does, then they go into compute similarities of context. And candidate entity 1, candidate entity 2, candidate entity 3. But the point is that these candidate entities, they don't derive from text. So word-to-vec style embedding learning thing. And what this paper shows is that it's possible to concatenate entity embedding approach, entity embedding representations which were obtained by running not2vec on a graph. And then you're going to have better results if you combine these representations in some of the cases. So what this really means is that this graph representations, they give you additional features, and the system is able to exploit both textual features, but also these graph features, and the prediction can be done more robustly. And in this case, the graph was actually a graph of Wikipedia entities connected by hyperlinks. So you have something like Michael Jordan as basketball player, and then you have NBA, and if there is a hyperlink from Wikipedia article about Michael Jordan to NBA, well, you're going to create this link. So this kind of a graph was used in this experiment, and it appeared to be useful graph for improving entity performance. Another task which was published is to the use of GCN autoencoder for taxonomy completion. So the task of taxonomy completion, well, is then you have some taxonomy, and then a new node arrives. Let's say you have a taxonomy, but the dog is not in it. So you kind of guessing where to attach dog. Should you like attach dog this place, or maybe you should attach dog to this place, or maybe you should attach dog to this place. So you don't know. And what this the system does, it actually uses fast text features to represent this unattached node, and it uses autoencoder trained GCN to encode to enhance this fast text embedding, and as you can see that it works to some extent, but also what helps is that it works as better than Poincare embeddings, which is another way to encode some trees or symbolic structures in vector space. But yeah, in some cases, simple not2vec is also sufficient to solve this task. And another article on this taxonomy enrichment has been published at the beginning of this year. And this is a similar idea that you have some taxonomy, let's say taxonomy of computer science, and then authors basically generate training example by generating from this taxonomy pairs of two things. So first is this ego network of anchor concepts, and then there's a query concept. So what they say, okay, for instance, we have this ego network, and then this is a query, and then, you know, given some feature of this, we, you know, if you provide a bunch of candidates here queries, then for the if we provide the correct place, then this network should get some output of, you know, positive class, and otherwise it should say, yeah, that's not the right place to encode it. And what they do, they encode this anchor concept ego network with a GCN. Some kind of actually modification of GCN from which takes into account the fact that you have some directionality in the nodes, right? So if you would just flatten all these relations, you will not consider the fact that this is a hyponym, so this is a more less specific, this is more specific, and they show that actually it makes a lot of sense to take into account directionality, right? Okay, so this is another useful application in NLP of these technologies. Another application is to extract relations. And here the authors rely on the distribution thesaurus. So this is a kind of a symbolic network where you have words as nodes and distributionally related edges. What this means is that you have crow related to vulture or animal, and what they use, they learn not to work on this graph. And then they use not to work features, and the features learned in this graph to perform prediction of the types of relations. So the original graph would not contain any types of relations, and then they would go into train a classifier which would take embeddings of this guy and embedding of this guy's input. Maybe it will concatenate them, right? And then apply something like as SVM on this concatenated representation, let's say owl, and then vulture. And then it would output 1 if the relation between these two guys is a co-hyponymy. And co-hyponymy is, well, it's a sibling relation. So if you have something like animal, cat, and dog, so the relation between dog and animal is a hyperonymy. But the relation between cat and dog called co-hyponymy. And so in this experiment, they try to predict whether the pair of words is cohyponymy or not. All right. So another relation is to use these embeddings, not embeddings, for natural language inference tasks. So this is a task where you have a bunch of a couple of sentences, and then you go into predict. So you have some function where you have sentence 1, sentence 2, and you're going to say that whether there is a logical. It's logical to say that from first sentence, the second sentence follows. Let's say I left the building and I'm on the street now, right? So if I'm at the building, then it's logical to that I'm on the street. But if I'm at the building, then maybe it's not logical. So, and though what they do, they integrate some features from UMLS. Which is medical taxonomy. Various different kinds of diseases, they are again structured using some kind of hierarchical network. So let's say you have different kinds of cancers, and doctors, they group these cancers according to like different types, and then they learn different embeddings on this representation. And what they show is that if you include this embedding from this knowledge graph, well, the performance basically goes up. And if you just use, fastText and Glove, then accuracy is less. So adding additional kind of structural information is useful to solve this class. Okay, so I think this is the last slide.